Another very simple problem statement. We want to find I of t, which is the current through the inductor with positive being in this direction for t greater than 0. So since we want to find I of t for t greater than 0, let's look at the circuit for t greater than 0. I like to redraw the circuit for the time that I'm interested in, because then I don't have to try to keep track of the position of the switch in my head. For t greater than 0, the switch is moved to this position. This source and this 15 ohm resistor aren't connected to the inductor, so I have a 5 ohm resistor, a 20 ohm resistor, a 1 Henry inductor, and another 20 ohm resistor. Okay, we have one energy storage element. It's an inductor and some resistors, so this is a first order RL circuit. There's no source connected, so that means this is going to be a natural response. So natural response of a first order circuit, the form of the solution, I of t, is going to be some initial condition I0 e to the minus t over tau. Since it's an RL circuit, tau is going to be L over the equivalent resistance seen by the inductor. Now all we need to do is find Req, determine tau from that, get an initial condition, and plug everything into this equation. So for Req, still for t greater than 0, so we're looking at this circuit, but we want to find a Thevenin resistance seen by the inductor. So take the inductor out and find the voltage current relationships across these terminals. This is all one node, so this 5 ohm resistor and this 20 ohm resistor interconnect the same two nodes, so they're in parallel, which I can verify by doing KVL around this. So the equivalent resistance for these is 5 times 20 over 5 plus 20, which is 4 ohms. Then after that, I have my Req. Here's 20 ohms. This became 4 ohms. Now any current that I put in here will also go through that. Those guys share the same current, so they're in series. So Req is equal to 24 ohms. And tau is going to be L over Req, so it's going to be 1 Henry over 24 ohms, which is 1 over 24 seconds. Finally, we need an initial condition. So we need I at t equals 0 plus just after the switch moves. An inductor can't change its current instantly. So this is the same as I at t equals 0 minus. So let's take a look at the circuit for t equals 0 minus. Just before the switch moves, I have a 12 volt source. I have a 15 ohm resistor that's connected to this 5 ohm resistor. I have a 20 ohm resistor. Now if I assume that this switch has been in this position for a long time, the inductor will look like a short circuit. And this current here is 0 minus. So these two 20 ohm resistors have an equivalent resistance of 10 ohms. So then I can calculate a voltage across these guys, V sub x. So V sub x is equal to 12 volts times, this is a voltage divider, 10 ohms over 10 ohms plus 20 ohms, since these two are in series and they have an equivalent resistance of 20 ohms. So V sub x is equal to 1/3 of 12, which is 4 volts. And this current is going to be that 4 volts over 20 ohms, so that's 4 volts over 20 ohms, which is going to be 1/5 of an amp. And we've already said that that will be our initial condition. So let me just make a little bit of room here. So taking this form of the solution and plugging stuff in, I of t is going to be I0, which is 1/5, e to the minus t over 1 over 24. So e to the minus 24t, that's going to be in amps, and that will be appropriate for t greater than 0. Now as usual, we want to check everything that we can. We can at least check the time constant and the form of the solution by writing a differential equation for the circuit, and that'll help us have confidence in this result. So to write the differential equation for t greater than 0, we want the circuit for t greater than 0. So for t greater than 0, the switch is in this position. The source and the 15 ohm resistor are not connected to my energy storage element, so I don't care about them for this. Now to write the differential equation, I'm going to want the voltage-current relationship across the inductor. Let's go ahead and label that on the diagram so that we don't lose track of it while we're getting our equations written. So if positive current's in this direction, my positive voltage terminal has to be here. The voltage is L di dt, so this is just 1 times di by dt because L is 1 Henry. Now we're down to just doing KVL, KCL, and Ohm's law. I can still combine these two resistors since they're still in parallel, just as they were in the last circuit. So this is 4 ohms, so 5 times 20 over 5 plus 20. So my circuit becomes, now if I use I as my default current direction everywhere, it's going to be going this direction in the 4 ohm resistor and this direction in the 20 ohm resistor. This will be my appropriate voltage polarities with which to apply Ohm's law. Now if I start here and do KVL, I have a 4 ohm resistor times I plus the voltage across the inductor, which is di by dt, plus a 20 ohm resistor, also times I, is equal to 0. Okay, well this is good news. This 0 here means that it's a homogeneous equation. So I of t is going to be I0 e to the minus t over tau, so we have the right form of the solution from our previous analysis. Now we can find a time constant by rearranging this equation. This equation becomes 24I plus di by dt is equal to 0. So this is 1 over tau is 24, so tau is equal to 1 over 24 seconds, which is the same answer we got before, so we can be pretty sure we're doing things right now.